G'day, I'm Pat and I do science for fun. In this video, I'll be using a CAD package to help illustrate how the Sun would be expected to move over the flat Earth. I will also look at some predictions of what would be observed from where I live in Sydney, Australia, if this model were true. Subsequent videos will further examine flat Earth predictions of solar behaviour and test them against reality. To start with, I'll need a scale model of the flat Earth. At the centre of the flat Earth is a North Pole. This will be represented as a point positioned at coordinates 0, 0 on the illustration. The South Pole is located 180 degrees from the North Pole. On the azimuthal projection map, which most flat earthers seem content to accept as a representation of their view of the Earth, this is a circle centred on the North Pole. As degrees are not a measure of distance, the rim of the world in this scale model will be represented as a circle with a radius of 180 millimetres, where millimetres will serve as a proxy for degrees. Halfway between the poles, the equator will be represented as a circle with a 90 millimetre radius. Finally, the Tropic of Capricorn and the Tropic of Cancer, 23.5 degrees either side of the equator, will be represented as circles with radii of 113.5 millimetres and 66.5 millimetres respectively. For any model of the Earth, the equator is a line on the surface of the Earth, essentially directly under the path of the Sun on the equinoxes. The tropics are the limits between which the Sun appears to move through the course of 1 year, with the Tropic of Capricorn essentially being followed by the Sun on the December solstice, and the Tropic of Cancer on the July solstice. As a reference aid, a line projected rimwards from the North Pole will represent a line of longitude. A quick Google search provides the latitude for Sydney, 33.87 degrees south of the equator. This can be represented by a circle centred on the North Pole with a radius of 123.87 millimetres. Where this circle and the line of longitude intersect will represent the location of Sydney on our model. This now gives us a rather simple scale model of the flat Earth. Consulting timeanddate.com for Sydney allows us to determine that between sunrise and sunset on the June solstice, we experience 9 hours, 53 minutes and 50 seconds of sunlight. For simplicity, we'll call it 9 hours and 54 minutes, or 9.9 hours, which, when multiplied by 15 degrees per hour, gives 148.5 degrees as the angle through which the Sun passes during the daylight hours. Inscribing lines from the North Pole to the Tropic of Cancer at 74.25 degrees either side of the line of longitude on which Sydney lies defines the path of the Sun between sunrise and sunset. The same steps for the December solstice results in a day length of 14 hours, 24 minutes and 43 seconds between sunrise and sunset. For simplicity, 14 hours and 24 minutes, or 14.4 hours, is multiplied by 15 degrees per hour, giving 216 degrees as the angle traversed by the Sun during daylight. Inscribing lines from the North Pole to the Tropic of Capricorn at angles of 108 degrees to the line of longitude defines this arc. For the 12-hour days experienced on the equinoxes, lines are inscribed at 90 degrees to the line of longitude. The defined arcs are traced and highlighted in orange for easy visibility, and the construction lines are removed. Looking north from any position gives the direction of the sun at local noon. Due to the vagaries of time zones, this is usually not exactly 12 o'clock, but it is the point in time which is halfway between sunrise and sunset, and the point at which the sun reaches its highest altitude on any given day. I'm yet to hear a reasonable explanation of what causes the sun to rise and set on a flat Earth. Some flat earthers seem to think it has something to do with perspective, and the sun being far enough away that it is beyond a vanishing point, where it can't be distinguished from the horizon. Others seem to think it's a limitation of our eyes, and that the sun is simply too far away to be seen, or that at some point there's enough atmosphere between us and the sun that it's obscured by haze. Whatever the reason, inscribing a circle centred on the point representing Sydney, with the radius set by the point at which the sun rises on the July equinox, sets the limit of my vision. On the plus side, the circle intersects with the point at which the sun sets that day. Yay! Score 1 for the flat Earth. Not so good is the fact that this circle is well and truly wide enough for me to see New Zealand to the east and the west coast of Australia in the west. Apparently, I can also see almost all the way to the North Pole, which would include Queensland, New Guinea, maybe a bit of Japan, and a fair chunk of Siberia. To the south, I can see to the Earth's rim and whatever lies beyond it. Maybe the ice wall obscures the view. Needless to say, I can't actually see any of those things, so for the sake of argument, I'm willing to assume that only celestial objects can be seen at those sorts of distances, and that terrestrial features are somehow smeared out to form the flat Earth horizon. But wait, the arcs representing the path followed by the sun on the equinoxes and the December solstice extend beyond the limits of my vision. I need a new vision limit which will encompass 14 hours and 24 minutes of daylight on the longest day of the year. So now it appears that the limits of vision are seasonally variable. Looking at the radii of the circles representing the range of visibility from Sydney, the inner has a radius of 123.669 millimetres, while the outer has a radius of 192.133 millimetres, an increase of about 55%. What flat Earth physics could be invoked to explain this radical improvement to Sydneysiders' visual acuity in summer? My range of vision on the December solstice is so long, in fact, that it now encompasses almost all the entire northern hemisphere. Inner circle. I did say that I would assume that only celestial objects are evident at such distances, so I'll refrain from asking why I can't see the Eiffel Tower. What I would ask, though, is why, as the North Pole is now comfortably inside my visual range, I still can't see Polaris. Polaris. Flat Earth's one weakness. Well, Polaris and gravity. And eclipses. And the lack of a functional map. I hope you found this video informative or thought-provoking. If you liked it, I have a couple of more ideas along similar lines, so keep an eye out for the sequels. I'll see you later.